This is the video presentation for the AELD Quiz 1. The members of the group are Sidharth, Madhur, Kumar, Sneha, Agarwal and Tarun, Sharma. This is the flow of the entire presentation. The APB protocol will be covered by me, AHB protocol covered by Madhur, and the AHB light protocol covered by Sneha and Tarun. So the APB protocol also stands for the Advanced Peripheral Bus, is optimized for reduced power consumption and minimal interface complexity. Even though peripherals can be connected via the AHB protocol, there are several advantages for using the APB protocol for this purpose. Some of the advantages include dedicated hardware, peripheral devices. So this leads to less load on the primary AHB system bus. It allows various frequencies of operation depending on the peripheral we are considering. And due to the limited functionality, a simple interface will lead to a faster design and verification process. There is an additional bus bridge that is used to connect the APB interface to the main system bus. And simple systems have normally have common clocks for both the AHB and the APB protocol, AHB protocol and the bus system itself. And there are two data buses, one for reading data and one for writing data. These buses can be up to 32 bits wide, but because these buses don't have separate handshakes, meaning these buses are not independent of each other, it is not possible to perform data transfer on both read and write bus at the same time. Here we have an example of various peripherals in the form of APB slaves. Via the AHB protocol, data is either being read or being written to one of these slave interfaces. In most cases, APB system has a bus bridge that acts as the bus master that connects to the APB to the main processor bus. In addition, an APB slave multiplexer and address decoder are needed, which sometimes is called which is sometimes used as a combined unit. So essentially, data is being sent from the AHB bus to the bus bridge, and then using this combined unit of data of the address decoder, we know which APB slave to send the data to, or to which APB slave to read the data from. This is a list of the various names that is used to refer to the signals that we'll be discussing in the APB protocol. Most of these signals will be discussed in the upcoming slides. Just for completion, we have the clock interface that is set, the select line to see which is a device we have to select to, the address, enable, and various more signals that we'll be covering in the upcoming slides. This is the write transfer with no wait states. With no wait states was first seen in the AMBA 2 protocol. So here, for a few things we didn't know about the APB transfer is that it must be of two states. The write data from the APB master must be valid for two clock cycles of the transfer in order for the transfer to be successful. At T1, we start with the P address, the PW data, and the P write, all being asserted at a positive clock edge. So here, at T2, P enable and P ready signals are asserted at the positive clock edge. So at T2, we can see that the P enable and P ready also are here, and now the handshake can take place as the slave itself is also ready to receive the data that's being written. And at the end of the T3, we can see that the data have been deasserted because the transfer has been completed and data has been written. As the data was, and as we know before, that this is not a pipelined protocol, and the data must be valid for at least 2 clock cycles. This type of transaction will be successful. So that's just the same thing that was just summarized here. So like the previously seen write transfer, this type of transfer differs as the number of cycles for a transaction to take place is longer. The reason for this is that sometimes APB slaves require more number of cycles to send the data. That can be due to some peripheral needing more time to respond to a particular prompt. So this was introduced in the AMBA 3 protocol, where we have wait states. So what we are trying to do is, in wait states here, the P ready is used to extend the transfer itself. So by keeping P ready low for 2 clock cycles, we're essentially extending the number of clock cycles that is used to completely write the data onto the APB slave. This ensures that the peripherals get a fixed 2 clock cycle access, and during the entire access phase, the data and the address does not change. It is also said that this type of system helps in lowering power consumption. Again, this is just a summary of what was said in the previous slide. This is the read transfer with no wait states, again introducing the AMBA 2 protocol. But here what we can see is that P address is provided at T1. Here we can see the P address is provided at T1, and the write signal is asserted to be 0 as we are not as we only want to be reading. And at T2 we get the data to be, we get the P ready signal to be high. So and so the first cycle is being completed, and at the start of the second cycle we get the P ready to be high. So the slave port must provide the data before the end of the read cycle, which can be any time between T2 and T3, and this will lead to a successful transaction. Again, as the APB is not pipelined, the two stages of the clock cycle here are needed. So this is a read transfer with wait states. Here the signal is extended by the P ready signal. It's asserted low, and during this time the access phase is going on and all other signals remain unchanged. This is again so that the slave has more time to respond to whatever address is being asked for. So this allows the unpipelined protocol to complete the data transfer, as it gives it more number of clock cycles. And at the end of the 2 clock cycles, when the data is available on the bus, we can finally read the data, and then we can deassert all of our other signals. So here only 2 extra cycles were given, but this again can be extended to many more cycles as and when needed by the various APB slaves. This is just a summary of what was said in the previous slide. So now we will move on to a response error. So this is for a write transfer. If what happens in the situation, we run into an error. So when an error response is generated, the read data from the AHB slave might not contain any useful information and could be discarded. The value of PSLVR, which stands for slave error, so this is the peripheral slave error, is only valid when the P ready signal is valid and not in the first cycle of the transfer. For example, if example of the slave error and the P ready signal are both high in the first cycle of transaction, this is not considered as an error response, as an APB transfer must last at least 2 clock cycles. So what this essentially means is that when this situation happens, when P ready and the slave error were asserted 1, this does not count as an actual error, because this is when the transaction just started, and the transaction must have at least been going on for 2 clock cycles. So if you consider this as the first cycle and this is the second cycle, when this situation arises again, so where the slave error was 1 and then the P ready deserted to 0 but again asserted back to 1, this technically counts as a error, and as you can see that the P data bus does not actually have any useful data, so we will have to discard this entire transaction. Similarly, for the read transfer, it's again a similar situation as the previous one. So here again no data is actually being read from the error, and the same situation applies to this, where at the first clock cycle, if both the P ready and the slave error are high, we do not consider that to be an error response, and yet data may not contain anything useful, and only consider the slave error and the signals also are high only when there are at least 2 clock cycles in the transaction have completed. We move on to the write strobe signal. That is also a feature of the APB protocol. So it's used for sparse data transfer. Each write strobe signal maps to 1 byte of data. The formula that is essentially used to calculate this is for P strobe, if we give the value P strobe of n, so n could be 0, 1, 2 or 3. The data that's actually being the valid data is essentially calculated by this formula, and that you can see by using this table here. The P strobe signal is an active high signal and is used for write only operations. During the read operation, the P strobe signal is ignored by the bus slave and the whole 32-bit is read. So this is another feature of the APB protocol, the protection unit support. In order to prevent illegal transactions, PPROT signals are used. There are different values the PPROT signals can take to determine whether a transaction is legitimate or not. PPROT 0, which is this particular case here, is normally used for the normal or the privilege, is used to decode for normal or privileged signal. When PPROT 0 is low, it indicates the transaction has normal access, but when it's high, it indicates it has privileged access. This is used by some masters to indicate the processing modes. A privileged processing mode typically has a greater level of access within a system. PPROT 1 is used to indicate whether the transaction is secure or not secure. Low indicates a secure access, high indicates a non-secure access. This is used in systems where a greater level of differentiation between processing modes is required. And PPROT 2, which is this one, is used for data or instruction access. So low indicates a data access while high indicates an instruction access. This bit gives an indication if the transaction is a data or instruction access only. Next, we will move on to the AHB protocol.
AHB is the high performance bus of AMBA specification, which allows high throughput data transfers, and it performs considerably better than other buses of bus specification like advanced peripheral bus, and just like any other AMBA specification, AHB also has multiple masters and multiple slaves, and it can and what allows AHB to attain this high performance is the burst transfers, ability for burst transfers, pipeline transfers, and overlapping of data phase and address or control phase, and wide width of data transfer that are supported by AHB. And usually AHB is used as a system backbone connecting the high bandwidth memory, ARM processor, DMA, on-chip memory, along with and there is a bridge to connect it to the APB bus. And AHB also allows multiple masters and multiple slaves to be served on the single bus. And so in this example, there is the AHB connects high bandwidth memory and the APB bridge as the slave, and there is this master which is the ARM processor and the DMA master, and there is a bridge that connects AHB to the APB so that the processor can communicate with the with the peripherals, and the peripherals can and vice versa. And there are many signals, but there are some signals that are always present in any AHB transfer. That is the address, which sends the address that needs to be written to, which will be read or written to, and there is this R data, which is the data that is read from the slave, and write data, which is the data that is sent by master to be written to the slave, and H ready, which indicates that the slave is ready to either write or read the data from master. And any transfer contains two phases, the address phase and the data phase. So the first of all, the address phase can be done in one cycle, and it sends the address that needs to be written to or read. And then there is the data phase, which sends the data or receives the data from the master as per the request. And data phase can extend up to can extend more than one clock cycles, and the data and the address phase are overlapped with each other. So first of all, there is the address is sent, and then the next address is sent, but at the same time the request for the previous address is served in the same clock cycle, and this way we are able to attain pipeline transfer. And the data phase, and if there is any delay in transferring of the data by the slave, then it deasserts its ready signal, and since the address and data phase need to be overlapped, the master cannot send its data, its slave cannot accept its address or the control signal that is sent by the master. So there is a stretch in the address phase as well in this case. And AHB supports 4 types of transfers. One is the idle transfer. So this H-trans signal is asserted by the master, which tells the slave what kind of a transfer it is trying to do. So one is the idle transfer, in which no data transfer. So the bus was just given, the master was just given the access to the bus, but there is no data to be transferred. And then there is this busy cycle, which indicates that there is the master will not be able to send any data in for this cycle. And then there is this non-sequential transfer, which indicates the start, which indicates the initiation of a transfer, and then there is sequential transfer, which indicates that a transfer can be completed seamlessly. And then these are the transfer types. So as I said, that the first transfer will be non-sec, indicating the start, and then then the master sends a busy signal that it cannot send the data right now. So the address phase cannot be completed in this cycle, but still the data phase for previous cycle can be for the previous address can be completed, and then in the next cycle it sends a sequential state, so the transfer can be completed, and it goes on and on, just like that. And then there is this burst transfer, so burst transfers are supported by AHB in a pipeline manner, and there are 8 types of bursts that are supported. The main ones are the single, which transfer only a single data, and then there is this incremental, which transfers unspecified amount of data from master to slave or slave to master. And then there is this incremental transfer, incremental 4, which transfers 4 bytes or 4 continuous data chunks. And then there is this in a continuous address, for a continuous address. And then there is this RAP4, which transfers 4 chunks of data, but the addresses for that data are but the addresses corresponding to those data are wrapped around along the address alignment boundaries. And the incremental transfer, for example, the incremental transfer, we send data 0x from 0x30, then sends 0x34, then 0x38, then 0x3c. But in a wrapping transfer, if the start address is 0x38, then it sends 0x3c, but after that you would expect that it should have sent 0x40, but instead of sending 0x40, it wraps around the address boundary and sends 0x30 first, and then 0x34, and this way the addresses are wrapped around in address boundary in wrap transfer. So this is an incremental bus, so non-sec, it is the usual AHB transfer, and then the data cannot be received by the slave, so it reasserts a ready signal. After that, and after 0x38, it sends 0x3c, and then it sends 0x40, so there is no wrapping around in case of incremental burst. But in case of wrap burst, there is a wrap around. After 0x3c, it sends 0x30 and then 0x34, so around address boundaries there is wrapping. For undefined burst length, first non-sec is sent, and then subsequent sec signal is sent, but it does not send how much data will be transferred. So how the slave knows is that the transfer has completed for the previous transfer is after receiving the first non-sec. After the previous transfer, it knows that the previous transfer has ended and the new transfer must go on. And the architecture of AMBA specification of AHB bus is like this. So there are multiple masters and there are multiple slaves, and there is this common bus which multiplexes data that is coming from the masters and demultiplexes the data from which comes from the slave. And the address decoding, for address decoding, first of all, the master sends the data. Whatever master sends the data, there is this arbiter which selects which of the masters will get access to the data to the address bus, and then we see that this whichever master has the access to the bus, its address is then transferred to all the slaves, broadcasted to all the slaves, and along with that, this address is also decoded by the master, decoded by a decoder to understand which of the slaves this address corresponds to, and this slaves needs to serve. So this H select signal selects if whichever H select signal is asserted, that slave is active for that particular transaction. And the master slave relationship is a bit different. So the master can initiate a transfer, but once it has initiated a transfer, it does not have much control over it. It must complete the transfer, and it cannot terminate it in between. It can delay it, but it cannot terminate it. And the slave has almost all the control in this case. If the slave is not ready, if the ready signal of slave is deasserted, then the master cannot continue with the transfer. And there is this H response signal which is used by the slave to signal the master that if there is what needs to be done. If there is this OK, then OK signal sent by the slave, then the transfer has completed. If there is an error signal, this means that transfer could not have been completed, and retry means that it asks the master to retry the transfer, and split means that master had lost access to the bus because and the split signal means that the slave is asking the master to resume its transfer. And the split transfer are one of the biggest features of this AHB protocol. So what it does is that since if the slave is not able to receive the data because it does not have the data that is requested by the master, or it does not have enough memory to store the data that the master is sending, then what it does is that it does not continue with the transfer. Instead it sends its it makes its ready signal low, and in this case the master will not be able to send its data, and it loses the access to the system bus. And after that when the slave is sure that it will be able to serve the master because it has the data that is requested, or it has enough memory to store the data that the master was sending it, what slave does is that it sends a split response to the master saying that the slave is now ready. Actually, the split response is sent to the arbiter. Arbiter sees that the split response is sent by the slave, and now the arbiter again grants the access to the bus to that particular master, and the transfer continues. Now the transfer continues to completion, and this is one of the ways that AHB attains its high performance.
The next protocol we have is AHB Lite protocol. So AHB Lite protocol is a single bus master protocol, and it provides high bandwidth operation. The most common AHB Lite slaves are internal memory devices, external memory interfaces, and high bandwidth peripherals. APB protocol is used for low bandwidth. Okay. Now AHB Lite, it is a single master protocol. If we want to support multi-master, we have to isolate them from each other. This results in a multi-layer interconnect. Okay. So in multi-layer interconnect, each master has its own peripherals which can be used. Basic thing, the descriptions, clock and reset, which are basic. H adder, which is the address bus data. HW, which is the write data. R data is the read data. H ready out, it is used to indicate finish bus transfer. H response, it provides additional transfer status. H select, it indicates select signal. HR data is the multiplexer receives the data ready and response signal from the slave. Now some of the transfer in the basic transfer that so after the first positive clock, so the master drives a signal which are sampled by the slave in this particular edge of the clock in basic transfer. The third edge of the clock, the master samples the output of the slave. This is in case of read transfer. In case of write transfer, the address phase remains the same with the sole exception that H write is 1, and the slave writes it into its memory. So in the following case, we have two wait states. For example, if the slave is not free, so then we have this particular wait state. Okay. So in this particular case, H ready goes down to 0, and after 2 clock cycles, you obtain the data. Now transfer types are decided by H trans signal. If it is 0, 0, it is ideal. It means that no data transfer is being used. If it is busy, it enables master to insert some cycles in the middle of the burst. And in non-sequential, it is in the when we are not doing burst, or we are doing first transfer of burst. Subsequent transfer of burst use sequential. So this is a particular case. So this is the first transfer. It is non-sequential. So in busy, processor does not want to read or write into that. So it pushes this transfer busy, and this is subsequent burst operations are sequential. In lock transfer, if the master requires locked access, it asserts H mask signals. When it is 1, the values go on in a continuous fashion. Okay, so typically it is not needed since the slaves read it in the order of the data sent. Now H size, it indicates the size of data transfer. Now for example, the value can be from 0 to 7. For a 32-bit bus, the values can be 0, 1, or 2. Okay. So in burst operation, we have two types, incrementing bursts and wrapping bursts. So incrementing burst, so basically it support 4-bit, 8-bit, 16-bit or incrementing burst. So in each of the time, we have incrementing and wrapping. Okay, so increment burst, it goes on until to access sequential locations. In wrapping burst, they wrap when they cause an address boundary. So address boundary is the product of number of beats, which is plotted by h burst, and transfer size, which is plotted by the h size. So this particular case, we have wrap 4 and increment 4. Similarly, we have various other operations. So in burst operations, we have a 4-bit wrapping. So now, since considering h size as a word, so it is 4-bit, 4 into 4 byte, which is 16 bytes. So it wraps around 16 byte, which is 0x20 to 0x3c. So from 0x38, it goes on to 0x3c, and then it wraps around 30 and 34. Naturally, the sequential and non-sequential bytes are given. There's also a wait state for the first transfer. In the second case of burst transfer, we have 8-bit incrementing burst. So the address increments every time. Okay, since it's a half-word operation, so it increments by 2 instead of by the default 4. The first one is non-sequential, and the rest ones are sequential. Now, in the case of weighted transfer, slave can use HAD to insert weighted state. Now, the master should not change the transfer type except when the transfer is idle or when it is in busy state. That is, if it's sequential or non-sequential, it cannot change the transfer type. So, for example, in idle, it is in this particular state. Now, when it is once it changes its state to non-sequential, it cannot change its state, or now it can change any of the values until HAD signal goes high. Okay, yeah. So in addition to that, master can change the address once during an ideal and after an error response. So the ideal transfer indicated in the previous figure. So the master changed it address during that particular phase, and then this particular case of an error is represented in the given figure, that it could change its state during the error phase. Now, what is the protection control? Now, in some particular case, we require some protection for a module, and the hprot value should remain constant throughout a burst transfer. This is not required a lot, okay, and this is used rather sparingly. So for the next aspect, I would like to take Sneha to take over.
Yes, thanks, Tarun. So the next thing we are going to talk about is address decoding. We have talked about signal names, data transfers, but how does AHB Lite know where to send the received data? To achieve this, it has a central decoder, and the address sent by the master, it takes as input. The decoder selects one of the slaves. The block diagram on this particular slide has 3 slaves. The responsibility of the decoder is to select the appropriate slave. Now, one thing to note is that the whole memory map should be filled. Each and every address must point to something. So if there are not enough slaves, it is necessary to add a default slave, or else there will be an error response generated whenever there is a valid transfer to one of the non-existent addresses. Moving on to the next slide. The block diagram here represents that once the data transfer from the master to the slave is completed, the slave generates a response which is sent to the master. Moving on to the next slide. So what is an error response? We mentioned an error response earlier, but what are its consequences? What is done after? The slide focuses on that. The signal of response from slave is named HRESP. This can be an OK or error. If it is low, means it is OK. If it is high, means it is an error. There's an error in the transfer. And this error takes an additional cycle, means that the error is minimum 2 cycle response instead of 1. If the slave requires more cycles to generate an error response, more number of cycles can be inserted. But how does the master know that it is done? So moving on to the next slide. We have an H-ready signal. Now this H-ready whenever this H-ready is high, means this is the last cycle of the error response, and the data in this cycle will be a valid data. Now, the H address means HADDR already has B here in wave diagram, which is represented on this slide. So that means the next address had already been fetched. Now, but we do not want this address. So we have to indicate that this is not a valid address. So H trans represents, gives a idle signal. Idle response, indicating that this is not a valid transfer. Moving on to the next slide. Data buses. Data bus width can be of different widths, 8, 16, 32, 64, and so on, but the recommended is 32 widths. SW data is for write and HR data is for read. There can be a difference in widths of slave and master and the bus. Now moving on to the next slide. So implementing a narrow slave and a wide bus. There's some additional internal logic required. We divide it into two halves and then feed a control signal to it so that it is converted into the 60 means the slave can get a 32-bit data. Now moving on to the next slide. Similarly, vice versa can also be implemented, that there is a 64-bit bus with the slave and 32-bit bus, and we can map the data starting with 0 to 31 bits HW data to HR data 0 to 31. It in between there can be it is divided into two particular halves. Moving on to the next slide. The last point in this presentation is clock and reset. Each AHB Lite component has a signal clock signal HCLK. All input signals are sampled on the rising edge, and all output signals must occur after the rising edge of HCLK. Reset is the only active low component in AHB Lite protocol. Moving on to the next slide. At last, we want to conclude this presentation with AMBA. Representing different protocols we have covered: AHB, APB, AHB Lite. AHB is high performance pipeline operation, bus transfers, multiple bus masters, spread transactions. APB is low power, large address control, simple interface, suitable of many peripherals. So AHB is connected to high bandwidth memory interface, but basically APB is used for different peripherals, which can be implemented in low power. AHB Lite is a reduced version of AHB protocol itself. Thanks a lot.